Welcome to today's webinar, where we're going to talk about metalens design, and specifically using effective index to reproduce a conventional lens system. So for a conventional lens, we're going to have refractive index values at different X and Y locations. So in the case of this graded index lens, we have a function that stipulates what the refractive index should be, or contributes to the refractive index calculation based on the X, Y position and the focus. The idea of a meta lens is to break this lens up into cells. Each of those cells has to have an effective index that would match this expression. Then what we do is we determine what to populate into that cell in order to get that effective index. The reference we're going to use is the Fresnel zone plate, or the Fresnel lens. And this is a lens that is designed based on the given expression here, which is a function of X, Y, the source wavelength, and the focus length. This goes into a cosine function, and then we apply a step function to the cosine. Anything above 0 is 1, anything below 0 is a 0. So then what happens is you get these concentric rings of high transmission, which is where the function gives back a 1, and is shown as white here, or low transmission, or no transmission, which are the black areas, or when the Fresnel function gives 0. The two reference simulations we're going to use for analyzing the effectiveness of our new design will be just an SI plate, so this will just be an SI slab, and then a Fresnel zone plate put onto that slab. All of the simulations that we'll be running will have a wavelength of 0.85 microns. The slab thicknesses will be 1.55 microns, and then the focus length for the lenses will be 8 microns. The zone plate, the SI plate design will just be the SI plate, and we're going to use that to demonstrate that without these lenses, there's no focusing. And then we're going to show a Fresnel plate and demonstrate the focusing. And then we will move on to the effective index approach. So most of this work is going to be done from within the product. So what we're going to do is we're going to open that up. We're going to make sure we're in Designer, and we are in the single simulation with the SI plate. So what we have here is a simulation set up with, I'll show you in the 3D editor to be a little easier to visualize it. We have a SI plate, we have a source located in behind it, and then we have two observers, a YZ observation area, and then an observation point located towards the end. Our focus on our analysis will be on the results from the observation area. The observation point is typically used for making sure that the simulation has been run for long enough. So for a CW simulation, you want to make sure any of the transients have gone away and you have a steady, stable simulation. Within this, we use parameters to set up properties that we think are going to be used across multiple things within a design. So for example, if we go up to simulation here and edit parameters, you will see that we have both width and length. This is the width of the simulation in the X and the Y axis, and then the length of the simulation along Z. Because the source and the observation area are going to use that width information, we make this a parameter so we can use that in all of the objects. So if you have to change it, you only change it in one spot. But we are not actually going to create each of these things in the same place here using the GUI. What we're going to do is we're going to do it using a script. So if we pop into the script tab, which is located, we have our layout view here, which is a 2D view down on the XZ. Down in the bottom, we have multiple tabs. We're going to take a look at the scripting tab. And this is the script I've written that will generate the, you see here, the plate, the input plane, and the two observation components. So in this code, it's set up so that all of the properties that I think I'm going to need to change from one simulation to the next are all located up at the top. So I just have to change them in one spot. I don't have to scroll through the code. Then in the main code, we simply call the functions that do the creates, and those helper functions are located down below. So for example, the input plane, we see we deal with the object manager. We create the object. It's going to be a rectangular input plane. And then we set all of its properties, its position, forward direction, its wavelength, and then down here, we set its widths. So this is done for each of the items. The plate simulation, as I said before, is simple. There's no structure other than this plate. And we should touch on the plate a little bit because the way this is done is a waveguide. It's not a rectangle, it's a waveguide. And the way we do waveguides is we have a profile and we have the waveguide. So within the waveguide, I'm going to show it through the GUI because it's just a bit more visually simple. So if I open it up, we have our waveguide, we have a start location, we have an end location, and then we have our width and our depth. But the cross section, the material information is stored in the profile. In this case, in WG example. If I hit the triple dot here, we'll see that profile, and we'll see that the 3D section is one layer, and it's treating it as silicon. So that's how we do our waveguides, and that's the gist of this simulation. The one thing that we do also change, and this is done from the GUI perspective, is the simulation parameters. So we have our resolution set to 10 nanometers. Note that this resolution isn't necessarily needed, this high resolution for this particular simulation, but with the rods and the size of those rods, this resolution will be necessary, and we want to make sure that we're running the same resolution for all three simulations. So we're going to use that. Everything else is pretty much set to auto. The one thing we do here that I want to discuss is the use of the non-uniform mesh. So if we hit parameters, we're going to go to the X, no changes, the Y, no changes, because it's pretty much uniform across the X and the Y, so we want to use the same values. But for the Z, we see here that most of this domain is air. So we can use just a straight lambda by 10, which should actually be 85 nanometers. But within the silicon, we need much higher resolution, and we're going to run 20 nanometers. So what we do is we set our maximum mesh size to be 70 nanometers, or 0.07 microns, and the minimum one is going to be 20 nanometers. And then what we're going to do is we're going to set up a zone for the minimum mesh, and we're going to run it from 0.5 to 2.05, which is the start and the end of this silicon slab. And just to confirm, we can see that we have a much coarser mesh away from the slab, and then as we approach the slab, it gets more dense, reaching its maximum density within the silicon. And then we would run this, and we already have those results set up for us here. This is the OptiFDTD analyzer. So OptiFDTD comes in two components. There's the designer, which you use to create the objects, and then the analyzer, which is where we process those results. We have the observation point, which shows the ramp up and any transients that are happening. And we'll take a look at those transients in a second. And then we see the simulation is pretty much steadied out. This is what we want to see for that observation point. You don't want to see that the simulation was cut off while you were still doing the ramp. So then what we're going to do is we're going to move over to the results we actually care about here, and we're going to take a look at the observation area. We see that our source did experience some transients and reflections, Fabry-Perot effects, within the actual SI slab, the reflections from the faces. So you want to make sure those reflections have gone back and forth a few times and things have steadied out, which we saw they did with the observation point. And the other point we want to note is that there's no focusing here. It's collimated, it's not diverging out, but it's not coming down to a specific observation point, which we expected. So we're going to pop back to Designer, and now we're going to look at our Fresnel example. And the Fresnel example is the same. It looks bigger, but that's just because it's zoomed. If we zoom in here, it's the same thing. What this Fresnel example is doing here is we have the SI plate, and then we are going to generate a series of cylinders, starting from the biggest one down at the bottom, and then moving up to be the smallest one. And the reason for this is the project browser is hierarchical, which means objects higher in the list take precedence over the ones in the bottom of the list. So even though this object here is air, this is object 0. If we look at object 1, it is set to be the SI, which means it's going to take precedence where that one exists. So when we pop into our scripting, so this should look familiar. It's the same as the plate simulation, with the exception of this piece here. So once we've created our plate, our input plane, and our two observers, we now decide the properties for those cylinders that we're going to create. And what we do is we create a series of cylinders from the largest value down to the smallest value, and we alternate whether they're going to be low transmission or high transmission. And each subsequent one will overwrite the one previous to it where they overlap. These radiuses are manually calculated. We could have done an equation within the script for it, but they were manually calculated. And what you do is you take the Fresnel expression, you identify the transition points where it goes from being a 1 to a 0, and you determine that those are located at the pi over 2 and 3 pi over 2 intervals of the cos function. So you can basically calculate what those correspond to in terms of radii, which is what we've done here. And then what we do is we alternate whether it's going to be low transmission or high transmission, and then we run a single for loop through those radii from largest down to the smallest one, and we create either an SI fiber or an air fiber. And what we end up with when we do that is a reproduction of the Fresnel zone plate. Let's take a look at the XY view of that. So it's going to take a moment here where it's going to render the refractive index. And this is the refractive index that the simulation will actually run. And we see here a reproduction of it. So we have at the core, high transmission, just air. And then we have these rings of high index. Now this differs from a ideal Fresnel zone plate, because a ideal Fresnel zone plate doesn't have a width, a thickness. So our zones of no transmission are actually zones of low transmission. We're still going to get some transmission through there, just not as much as if it had have been just air. So we are expecting our Fresnel zone plate to be off from the ideal case, which is why we're doing this as a reference, so that we can compare the reference one to the effective index one, instead of trying to compare the effective index to the ideal no thickness plate. So that's the script for that and the general design. If we pop over to the results, so this is the Fresnel lens. We can see the same structure, check our observation point. It has pretty much stabilized, which is what we were expecting. And then when we check our observation area, we can see that we are definitely getting focusing at roughly the 8 micron spot. In order to confirm that more specifically, we're going to do a Z cut or a horizontal cut on this. So we're going to hit the horizontal cut, and it's going to show us the results of the E field, the EY field in this case, at a specific Y value. And we want it to be at the center of this particular cut observation area, which is at the 0. And we can see that we definitely get a peak located at roughly 8 microns. In this case, it's 8.19. So if this was an ideal Fresnel zone plate located at 0.5 microns, we would have expected to see focusing at 8.5 microns. But A, this is not an ideal Fresnel zone plate, and B, because of that thickness, the effects are happening over a range. So we actually see focusing at 8.19 microns, and we see the focus point is actually quite broad. It's ranging from roughly about, if we do the full width half max, you're looking at somewhere in the range of about 7 up until about 11. So those are the results for there. And we come back to our slide deck here. So these are those results presented again. Now that we have established these two references, what we're going to do is we're going to take a look at how we might create this using an effective index approach. So what we're going to do is we are going to have the same setup. We're going to have 0.85 micron source. We're going to have a 1.55 micron SI slab, and then we're going to have a focus length of 8 microns. But what we're going to do is anywhere where we want high transmission, so low index, we are going to generate an array of air holes that are 0.2 microns in diameter and have a lattice constant of 0.25. And the idea being wherever there are air holes, our index is lower, we have a high transmission zone. So we can see here on the left, we have high transmission zone in the center, a low transmission around it, high transmission, low transmission, in the same pattern that we saw for the standard Fresnel zone plate. So we're going to pop over to Designer and show how that looks in terms of the scripting. This is still Analyzer. We pop back to Designer, and we're going to take a look at the effective index Fresnel zone plate. So what we see here on the left is a very large number of waveguides. Each one of these is one of our air holes. So if we take a look in our scripting, we see, again, very similar code here. This is all similar to the other ones up until this point. Instead of creating concentric rings, what we have is a nested for loop, so 2 for loops together that sweep all along the X points and all along the Y points in steps of 0.25, which is our lattice constant. And at each one of those XY points, we're going to calculate the Fresnel expression. If it comes back as a 1 or high transmission region, we are going to create a rod. And if it's not, we do nothing. So that's where we get all of these air holes generated from. The Fresnel calculation is one of the helper functions. It's down here. So we have the Fresnel expression right here, which is an exact duplication of what we saw in the slide deck. So we have the cos, which is a function of the XY position, the wavelength, and the focus. And the feedback, the results from that cos function are fed through a step function. And the step function is defined here. We run that, and we get these air holes. Now, one thing I want to comment on in terms of OptiFDTD scripting is there are technically 2 ways to run a script, or ways to see a script. One is to use the script to generate your layout, which is what we're doing here. These scripts are not running these simulations. What's happening is when you run the script, which is this plus button here, you are actually generating the layout. The other way of running a simulation or treating a script in OptiFDTD is for the script itself to actually trigger the simulation. So you make a call within your script to trigger the simulation. And then when you open up your simulation settings, you would stipulate that you want to simulate using the script. And in that case, you would need that simulation call within your code. That's that. I'm going to pop over to the 3D editor just to give you a view. So this is what we're looking at. We have air holes where we want high transmission, no air holes where we want low transmission. When we run this particular simulation, what we're going to find is a very similar result to what we saw with the Fresnel plate. So again, we have focusing in and around the 8 microns. And if we do our horizontal slice, we can see that the focus point is, again, located in and around the 8 micron. In this case, it's 8.22 microns. With the Fresnel zone plate is 8.19. And again, we see that the focus point is actually quite broad from about, again, from probably about 7 out until about 10. But it is much in line with the Fresnel zone plate example that we showed, as opposed to trying to match it to the ideal Fresnel zone plate. So that's the simulation results. I'll also show the observation point, where again, we see that the simulation has been run for long enough that the simulation has stabilized. Coming back over to the presentation, these are those results again. I'm just going to show the citations that were used for the designs that we did. While we have that up, I am going to take a look at the questions here that we had. There were two in regards to scripting that I will touch on. I'm going to jump over to the product and make sure it's actually the designer. So the first question was, can we actually access the parameters I mentioned earlier, the width and the length, from within the scripting? And the answer is yes, we definitely can do that. It would be problematic if it wasn't. So you'll see in the scripting, there's two spots where I grab the length and the width. So there's two ways of working with parameters. One is to do this evaluate expression from the parameter manager, which will give you the value for length or width, and then to use those as variables if you need them within your VB script. The other way to do it, and you'll see it throughout the other functions, is if we take the observation area, for example, here, I define its position based on the length of the domain, and I don't actually use the length variable. I actually use the parameter. That's why this is in quotation marks. I'm giving it an expression. So when it goes to the simulation engine, it will evaluate that expression. So if the parameter is changed between me writing the script and me running the simulation, it will use the right parameter. You'll see that with the dimensions of the observation area as well. And you'll see this for the observation point. In this case, I use the variable, but down here I use the parameters. And the second question we got in terms of scripting was, what's the best way to learn these scripts? So if you go to help topics, you'll get all of the documentation from the products. There is a full PDF breakdown of all of the functionality that can be called and used within VB scripting. So that's one thing. The second thing that you can do is to use layout script. So these are buttons that help you generate scripts. So what a layout script will do is it will go through the project browser and create script for each of the objects that we have. So this script that you're seeing here is a cleaned up, modified version that I created so that I could reuse it for other ones. But if we wanted to learn, for example, how to generate an input plane, what you would do is you would select layout script. It's going to warn you that it's going to overwrite the script. That's fine. We hit yes. And now what we see is a simplified just feed an output with scripting. So here's the script for an input plane. And now we know which properties we can access. Those are all in the PDF document I mentioned before through the help, but it's handy to have this and then edit from it. Somebody's asking the difference between this and a Fresnel zone plate. So as I said before, an ideal Fresnel zone plate has no depth. It's either transmission or no transmission. Whereas with our structure, we do have a depth and there is some transmission in the no transmission zones. It's a lower transmission zone for this. So we weren't expecting to match the ideal zone plate, but the idea here was not to do that. It was to use an effective index approach to reproduce the results of something that was not done with an effective index, which we did do. Just bear with me a moment here. I'm looking at the questions. I believe that's everything we're going to address today in terms of the questions. If anybody has any technical questions, please feel free to send those questions to support@optiwave.com and we can follow up with those as needed. And the other item I would like to touch on is we offer 30-day evaluations of all of our products. If you want to get into trying OptiFDTD and doing some of these lens designs, you can certainly do so. If you go to optiwave.com and you go to the free evaluation link that's in the top right of the webpage, it'll bring you to our forum. Just set up a forum account, which is free, and you will be able to download the product. Once again, thank you for joining us for this webinar, and have a good day.